Okay, hopefully you can see that.
Yeah, you are live, looking good.
Right.
Wednesday,
Okay.
12th of November. So yeah, here we go, everyone. So this is going to be our final session with Laurence from Extra.pio of this 4-part series. Hopefully it's not a final session forever, because I don't know about you guys, but I really enjoy these. And yeah, I mean, this is it. You know, we had Tom Dwyer last night taking us through a nice smart contract implementation, also with a user interface, which displayed some nice useful data. Got exposure to Ganache, Truffle. So essentially the key tools of the toolbox. And I'm sure Laurence will take it on from there tonight. So thank you once again, Laurence, and we look forward to it for the next hour or so, or 2 hours.
Great. Thanks, Brendan. Yeah, thank you for inviting me back again. Yeah, I look forward to, hopefully we'll do some more. But today's session is more about some associated technology that goes along with blockchain, but also a chance for people to ask questions as well if there's anything we've covered that you want to know more about or you want some clarification about. I don't think will last the full 2 hours this evening. I'm going to skip through some of the details in the slides because it does get quite complex. But yeah, if you have, please do ask questions as we go along. And if you questions from today or any of the previous sessions, I'm happy to answer those. Okay, so there's our details. If you about my company, if you want to get in touch with us, you've got the details there. So please use those. Happy to hear from people. So what we're going to cover today is some associated technology, and the reason I've chosen these is that they're often used alongside blockchain. They're not blockchain technology per se, but they are used either that these technologies may use blockchain, or they're often used along with projects that use blockchain, or they are used to help solve some of the problems that blockchains face. And if you're thinking of working or researching in blockchain technology, then you'll definitely come across these areas. So it's useful to have an idea of what they are about. And also, there's the formal methods as well. I shall mention. Someone asked about that last week, so I'll just briefly touch on that. I don't know a great deal about it, but I have got some resources there that people can follow. And then finally, other useful resources and where you can go next to find out more about researching or developing on the blockchain. Okay, so let's start with the first technology I want to talk about, homomorphic encryption. The idea of fully homomorphic encryption is often described as the holy grail of cryptography, and people also talk about somewhat homomorphic encryption where the technology hasn't quite got there yet. But the idea behind it, and it is quite an intriguing idea if it can happen, is that a user will have some data that is in plain text, and that they want to perform some computation on this data, but perhaps they don't have the computational power to do this themselves. They want to give this to a service that will do the computation for them, but they don't want this service to be able to understand their data. They want to keep their data private. So the idea behind homomorphic encryption is that the user can encrypt the data using some kind of encryption scheme, can pass this to a computation service. This computation service will do some computation, some operation on the data, and then pass it back to the user, who can then decrypt the result of this computation and get back a result that makes sense to them as plain text, and is the effect of if they'd done the computation themselves. Of course, whether this can happen is very much dependent upon the encryption scheme and the complexity of the computation that can be done. And so I think we're at the stage where for some common encryption schemes, there are some operations, some computations that can be done relatively easily. So we can perform this, we can do this. For example, I knew someone at college who did their DPhil around using these kind of techniques to encrypt medical data and then perform statistical analysis of that data. But the analysis was done on encrypted data, so there was no chance of any private medical data being leaked. You can see it in some very simple ideas. If you think in just numbers, where your encryption scheme is to just double a number, you can start off with wanting to perform the calculation of 3 plus 5. If you encrypt that by doubling those, you get 6 plus 10. If you perform that computation on the encrypted data, you get 16. You then decrypt it by dividing by 2, and you get back the answer 8, which is what you would have got if you'd done the calculation yourself. So intuitively, it's quite a straightforward idea, but in practice, it can be quite difficult to achieve, as I say, particularly if you want to do complex calculations. And there are a number of applications for this. As I mentioned, the analysis of medical data. People also have used it for preventing satellite collisions, because nations may, obviously they don't want their satellites to collide with each other, with other nations' satellites, but maybe they don't want to give away the positions of all their satellites. So you can use this to pull together data. You can encrypt the location of your satellite and then check whether there's going to be collisions without giving away the details of your satellite's location. And also just general machine learning on encrypted data. So a very useful general technique. The second technique I want to talk about is proxy re-encryption. And I came across this via the company NewCipher and their key management system. And I found this useful when I was working on a particular blockchain system. And it was a way of handling key management. I mean, generally when you're writing applications, and particularly blockchain applications where you will have keys that you want to manage securely and efficiently, key management can be a problem. And this was a way their system was a way to do that. I know when I speak about this, people tend not to be over impressed by this technology. I think it's quite useful, but well, we'll see what you think. The idea behind this is that Alice has some data and she's going to encrypt this data, but maybe she wants to selectively share this data with other people. So perhaps she wants to share it with Bob or other people. But it may be that the encrypting this data may be more computationally difficult or may require more effort than she wants to put in. And so she would like a proxy to handle the encryption of this data. And what proxy re-encryption allows Alice to do is to start up with her plain text, and she encrypts this with her keys and gives this to a proxy. And so the proxy has the encrypted data, does not know what it is, and Alice has not shared her private key with the proxy. She can then ask Bob for his public key, and she can then create what is called a re-encryption key, which she does by using her own private key and Bob's public key. She can send this re-encryption key to the proxy, who can then use this to re-encrypt the data. So the data that is already encrypted, that Alice already had encrypted, can be re-encrypted by the proxy, by the third party, and sent to Bob. And then Bob can decrypt the data with his private key. So this means that Alice has effectively, given Bob access to this data without giving away any knowledge of her private key. And this has been performed by a proxy, again, without the proxy having any knowledge of either the plain text data or Alice's private key. And NewCipher built this system, and they did it as they've done it effectively in a blockchain. So there are nodes that are proxies in their system, and they can be rewarded with cryptocurrencies for performing re-encryption. And we'll do this on behalf of people who want their data to be re-encrypted and shared. And I came across this particularly on a project I worked on called MedicSane, which was around using sharing medical data on the blockchain. It didn't really get very far. We did write a paper, but it didn't really take off. But the idea with this was we wanted to store data on IPFS, and we spoke about IPFS yesterday. So this is a file system, the interplanetary file system, a decentralized storage mechanism, but it is a public system. And if you put data on there, it is possible that if other people know the address of this data, they will be able to read it. So if you're going to use it for potentially sensitive or private data, you would want to encrypt that data before you add it to that storage. And what proxy re-encryption allowed us to do was effectively add data onto IPFS, but do it with really a random key each time. So the proxy is effectively re-encrypting the data with random keys all the time and storing. So this is stored on IPFS, but it's the keys to store this data is not just one key. So if there's any compromise, someone would only ever get access to one piece of data. The other pieces of data will be stored with different keys. But the key management system means that we can easily decrypt the data ourselves. So for systems like that, I think it's very useful. And there have been some startups that have used this. There's some links to some there. There's another one some friends of mine have done called Privacy, which tackles the sharing of private data and GDPR using proxy re-encryption. Okay, so that's the second technology. That can be taken a little bit further with threshold proxy re-encryption. So NewCypher further developed their libraries into the idea that rather than one node having this ability to re-encrypt, you may spread this out over a number of nodes, and there would be a threshold of nodes that would perform this encryption. If you're interested in that, there's a paper there. Their project is called Umbral. They've also just brought out and been doing research and brought out a project that allows re-signing of data as well, and uses similar kind of schemes, but rather than just encrypting data, this is all about signing data. So if you're thinking in blockchain terms and thinking of transactions being signed, it's a similar idea to that, but allowing re-signing of data and threshold re-signing of data. So very interesting technology, well worth looking at. Okay, I'll go on to my really my favorite topic, which is zero knowledge proofs. All of the technologies I've spoken about, and this one, often I think they seem like magic when you talk about them. And even though I have been through the mathematics involved with these, and I appreciate that it makes sense, and that there's nothing hidden really, and it's all not straightforward, but it all makes sense, and it still seems like magic to me at times, and particularly zero knowledge proofs. It's quite a strange concept, and yet it's an extremely powerful concept, I think. The idea behind it is generally there are two main actors. There may be a third one, the creator, but often the prover is also the creator. And similar to in the cryptography world where we talk about Alice and Bob, these two actors are often called Peggy and Victor. And the simple idea behind a zero knowledge proof, and particularly where we're talking about privacy, is that the prover, Peggy, has knowledge of some secret and wants to show that she has knowledge of this secret to Victor. So Victor is our verifier. So she wants to prove to Victor that she has knowledge of a secret, but without revealing any details of that secret to Victor. In fact, with a zero knowledge proof, it goes further. The only information that Victor should receive in a zero knowledge proof is the fact that Peggy has knowledge of this secret, and that is all they should receive. It should be just one bit of data. And a nice example, an intuitive example of this is if you know the Where's Wally books or the Where's Waldo, I think in the US. These are children's books where a character is distinctively dressed in a picture amongst a mass of similar looking people. And the idea behind it is to try and find Wally within this massive picture. And if you imagine that you're playing this with someone, but this person you're playing with is inclined to cheat, and you know that if you point out the fact that you found Wally in the picture, they will say that, oh yes, they knew that's where Wally was all along. So what you would like to do is to prove to them that you know where Wally is without giving away the actual location of Wally. And a way to do this is to take the book that you have and then take a large piece of paper. So the piece of paper needs to be much larger than the book. And in that piece of paper, cut out a hole that is the exact dimensions of Wally in the picture, and then put the book under the paper and then position Wally beneath the hole so you can show to the other person that indeed there is Wally through this hole in the book. But if you've done this well enough and the piece of paper is big enough and you haven't shown them where the book is in relation to the rest of the paper, then you will have obscured where Wally is actually in the picture as a whole. So you will have, Peggy, your prover here, will have proved to Victor that she knows where Wally is in this picture, but she hasn't shown the location of Wally to him. She hasn't disclosed that information. And it's curious that we can have a proof like that is purely really mechanical, I guess, and just involves pieces of paper and books. And yet we're going to use similar ideas and similar motivation to do things in cryptography and to do very elaborate mathematical proofs. Another example, again, I'm using some very intuitive examples here because it's quite difficult. There's quite a difficult balance to strike between describing zero knowledge proofs in a very intuitive way and then going through the maths in a lot of detail. So I'm going to try and do a mixture of each in the hope that I can give you a flavor of both, but without losing people in the maths, which does take a while to really get your head around. But another good intuitive example is the idea of the color of some billiard balls and a verifier who is colorblind and so cannot distinguish between a red and a green ball. And I've got a typo in my slide here. Yeah. So the prover here, Peggy, is claiming that she can see the difference. She claims there's a difference between these two balls, but Victor cannot see this difference, and in fact does not believe that there is any difference. And so it's up to Peggy to produce this proof to Victor that there is indeed a difference and that she knows it. And the proof has to be something that Victor will accept and will convince him that she has this knowledge. And so one way to do it will be for Victor, the verifier, to take these two balls and to show them to Peggy, one in each hand, holding them out in front of him. And then he puts them behind his back and he may choose to either swap them over between his hands or not to swap them. And then he will bring them out again and ask Peggy if they have been swapped over or not. And then, of course, every time that he asks this, Peggy will be able to say whether he swapped them or not. And if she were guessing, there would be a probability of a half that she would guess correctly each time. So imagine that Peggy does indeed say whether he has swapped them or not. The first time, I guess, is correct because she can see a difference between them. Then Victor may say, okay, maybe you guessed that time. It was even odds that you would have guessed correctly. So we'll repeat the process. So there is an iterative proof going on here. So he does the same thing again. We have a second round here. He brings them out again, asks Peggy if they've been swapped over or not. And Peggy again answers and correctly says whether they have been swapped. Now, depending on how much faith Victor has here, he can repeat this process a number of times, but eventually he will no doubt accept that the probability that Peggy can have successfully guessed the answer correctly each time is vanishingly small. And so eventually he will concede this proof, this iterative proof, that Peggy does indeed know that there is a difference between these two billiard balls. So this is a proof, but it is an iterative proof. But it is also a zero knowledge proof, because at the end of it, Victor has been convinced of this proof, but he has not gained any knowledge about these two balls, other than that Peggy does indeed know that there is a difference between them and that she can distinguish between them. Okay, so that's the second one. There are other examples. There's one here about age. I won't go through it. It's really just a very similar thing. Again, very mechanical ways of doing these proofs. Now, to go into it in a little more formally, what we want to do is to create a proof system but also have zero knowledge. So what do we require of a proof system? And if we look at the history of research, mathematics people have been talking about proving things and proof systems before they were thinking about zero knowledge. And really, it's we're taking the idea of proving systems and then adding the zero knowledge requirements on top of that. So what we require of a proof is that there should be two things. One is completeness. And this means that if the prover is being honest about the proof, that they can convince a verifier that is honest of a correct proof with a high probability. So if Peggy is being honest in her proof, and she will be able to convince an honest verifier that this proof is true to a very high probability. In all of this, we are dealing with probabilities, so all of the proofs are given as being to a very high probability. And then the second aspect is the one of soundness, and this is really, I guess, looking from the other aspect, that if there is a false proof, so if we have, say, a dishonest prover, that they will not be able to convince a honest verifier of an incorrect statement or an incorrect proof. And there's details here about the super polynomial time and polynomial time. This is just really in the formalism of these things and to show some of the bounds in computation that are involved here. For what we're talking about, it's not really something you have to worry about. It's really just saying that there are bounds to the amount of computation that feasibly these people can have. And when we're talking about these systems, we're not necessarily thinking that somebody would have unbounded time or unbounded computation. So that's those two are really all about our proof system. And then to that, we add this third requirement of zero knowledginess. And that really is that our proof, when we've done this proof, when we've presented it, and this proof, as we shall see, is just a piece of data, really, a sequence of numbers, along with some checks that the verifier can do. But once they've done this, that the verifier will gain nothing more than the fact that the proof is either true or false. Okay, and there are different types of zero knowledge proof. The zero knowledge proofs were really invented, I guess, invented in the 1980s, in the cryptographic sense anyway. And there have been many different attempts to, or mechanisms to produce them. These are the names of some of the types. People have tended to make them similar, so SNARKS, SNARKS, Bulletproofs. But it's quite difficult when you're talking about these to get a good taxonomy of proofs, because often if you look at projects, people will maybe mix and match various cryptographic primitives in different ways, or use little bits from different types of proofs together to make a zero knowledge proving system. So it can be a little bit difficult to navigate around the research in this area. At the moment, most of the research and most of the projects are are going on in SNARKS, particularly since 2016, 2015, 2016 time. But then there are, as I'll say, improvements on those. Often, though, you don't have to go. I mean, I'll talk about SNARKS in much more detail. Often, you don't have to go into as much complexity as those. As we shall see, you can do things with very simple cryptographic proofs. But at the moment, certainly in the blockchain world, zero knowledge SNARKs and STARKs are very much the preferred techniques at the moment. Okay, so I've used this term SNARK. What does it mean? It's just an abbreviation for a succinct, non-interactive argument of knowledge. To explain the non-interactive part first, when we were talking about the example earlier with the billiard balls, that was an interactive proof. But what we are trying to do, we don't really want that to have to go through that process of having the prover and the verifier communicating many, many times. What we would like is to just do this once and just allow Peggy to present one proof to a verifier who can then verify it, and that will be the end of the process. So that is why they're non-interactive. Succinct, because we want this to be practical, we want the proof to be of a reasonable size. If the proofs were terabytes of data, then that would not be feasible, particularly in the blockchain world. So we want the proof size to be relatively small. The argument of knowledge is just really a mathematical distinction about that. And yeah, we don't have to really go into that. It's slightly stronger than, so a proof or an argument, it's just slightly different in the one is we're saying that we don't just know that a statement is true. We don't just know the statement is true. We also know the secret behind this. So some secret inputs to our proof as well. Okay, so this is a process flow. So Socrates is a project that you can use within Ethereum. So if you remember when we were looking at Remix and we had a number of plugins, one of those plugins allows you to use this tool called Socrates, and it is a way of being able to create a proof and have the verification done in a smart contract. So it's a way to get zero-knowledge proofs onto the Ethereum blockchain. But I'll just talk about, we won't go into that. I'm not going to show you that this evening. It will take too long. I'm just going to really describe the flow that happens when using a zero-knowledge proof, and particularly SNARK. So for this, the creator, which could be the prover, creates a program in some language, a higher level language. And then we go to a step that's called the trusted setup. And I'll be talking about the trusted setup more in a moment when we talk about different types of zero-knowledge proofs. But this is a step that needs to be gone through before the prover and the verifier can use the zero-knowledge proof. It's a computational step that produces data. The prover then creates two keys. Now, these are not thought, shouldn't think of these as keys in the sense of public-private key pairs. They're just things that are used by the prover and the verifier in the later stages. The two keys are, one is a proving key, one is a verification key. So the proving key is used to create a proof. The verification key is used in the verification of that proof. So once these keys have been created, the proving key is kept by the prover. The verification key is given to the verifier. The next step then is that the prover does a thing called computing a witness. Now the secret in a zero-knowledge proof is also called the witness. In Socrates, there is a step where you do a small computation where you effectively put this secret into a piece of data. So it's really a step that is more particular to Socrates than to generally in zero-knowledge proofs, but generally in a proof, we do have, of course, you have this idea of a witness, some secret that the prover has that they want to show that they have this knowledge of to the verifier. And then the prover generates a proof using the proving key that was generated in the trusted setup. And this proof will then, this proof needs as an input the witness, the secret. But once computed, from the witness and from the proving key and from potentially some public inputs as well, once this is computed, this proof cannot be used to find out what the witness was. So even with feasible computation, you cannot get back to the witness from the proof itself. You can only use that, you can only verify that that proof is true. Okay, just to look at that as a diagram, you create some algorithm that defines the thing you're trying to prove. That gets, you run a trusted setup, put this into a mathematical representation. This produces two keys. You take your secret or your witness along with a proving key to create a succinct proof, which you give to the verifier, and the verifier with the verification key can then check that the proof is true or show that it is false. And in Socrates, there is this ability to have the verification done within a smart contract. So effectively, you could have this on the Ethereum blockchain, you can have this in a contract, and then if people are interested and want to know that your proof is true, you can send them the proof via some side channel, and they can then input the proof into the contract and verify for themselves that your proof is correct. Okay. I'm going to go into just a little bit more forward here, just because it introduces a term that we need to know about. Going back to the beginning of this process and what we are doing when we were creating these keys, I've said we have this trusted setup, and so we have the idea of these algorithms that are producing the proofs and verification, but also this idea of the creator that we're using, where we take an algorithm that holds our proof, or how our proof works, and then produces proving keys and verification keys from that. And the first step in that process is the thing called a trusted setup. And this trusted setup also takes a parameter lambda. And now, when this was being done, when the research for this was being done, this was not really regarded as much of a problem, the idea of this secret parameter lambda. It was just part of the setup. But when this has been done practically, this has proved to be quite problematic. And the reason for that is that if this secret parameter lambda that was used in the setup, if that was to leak, then people would be able to create false proofs. So when we're going through this trusted setup step, we have to be sure that we do not allow other people to find out what this secret parameter lambda is. And indeed, when this was done in cryptocurrency Zcash, this became known, this secret parameter, this lambda, became known as toxic waste. And so when we look at projects that are doing this, that are using zero-knowledge proofs and creating proofs and creating proving keys, and do this trusted setup as a first step, they have this problem of this toxic waste. So they wanted to be able to do a trusted setup without giving away details of lambda, the secret parameter. And the way that this has been done in practice involves certain ceremonies. Now, I mentioned the project Zcash. This is a cryptocurrency that uses zero-knowledge proofs, and we'll look at that a little bit later. And they were really one of the first large projects in the blockchain space to use zero-knowledge proofs. And they had a ceremony when they first came online to do this trusted setup. And the way they did it was via a shared computation. And the idea behind this shared computation was that this shared computation would be done to produce these proving keys, and the computation would be done by a number of people. And if the computation, if just one of these people doing this computation was honest, then the whole computation could be regarded as being honest and have succeeded. To say that in another way, the thing would only be dishonest, so there would only be the chance that this toxic waste would have leaked, or this secret parameter could be found out and used by people, would be that if everybody involved in that ceremony were dishonest and colluded with each other to find out this secret parameter. So effectively, when they did this initial ceremony, they were saying to the world, and I think initially it was only a handful of people that were involved in the Zcash ceremony, but the initial one, they said to the world, effectively, if you trust just one of these people to be honest, then you can trust that our setup has been done correctly. Now, later on, they did a second setup and they increased the number of people involved. So over 100 people were involved. And they did some very interesting ways of doing the computation that was needed for this setup. And people filmed themselves doing their part of the computation in various different ways. Some people got laptops and filmed the computation being done and then filmed the laptop being destroyed afterwards. One person took some radioactive material from near Chernobyl and then used that to generate some entropy as being the input into their computation, and used that as being proof that it was being done correctly and there was randomness in their computation. Lots of people did things in different ways and lots of fun ways to make the process interesting. More recently than that, there's a project called Aztec. So they're a zero-knowledge proof project on the Ethereum blockchain. And about a year ago, they had a ceremony to do their trusted setup, which they called the ignition ceremony. And they allowed people all around the world to be involved in this computation and do part of this computation, so that altogether this form their trusted setup. We were lucky to be involved in that, and the whole thing took a few weeks. There were a few hundred people involved doing this computation. The first person who did it was Vitalik Buterin, the inventor of Ethereum. I do think that given that he is quite highly regarded and quite well trusted, that we could have stopped at that point and said, well, generally everybody trusts Vitalik anyway, so we'll trust it was done honestly. But no, everybody did take part. And again, it was the case that as long as there was one honest person in that ceremony, then the whole ceremony was valid and the setup worked correctly. Okay, so as you can see, this idea of a trusted setup is quite perhaps an onerous procedure, and the different types of zero-knowledge proofs, some of them have moved away from doing the setup and try to find ways that they can do a zero-knowledge proof without this setup because of the amount of computation and organization that has been involved. I would just like to add that I think on the flip side to that, it is good that there is this ceremony going on, in the sense that it does build a community around the product or the project, which can be quite fun. But no doubt it is quite a lengthy process and does involve a lot of people and a lot of time. So this generally is needed if you're involved in a project that uses a ZKSNARK. And this is because the SNARKs, the research that was done into them, there was a paper published in 2016, Groth 16, which made a major breakthrough in creating SNARKs and made them much more practical. But this came along with this trusted setup. So that in order to use these or use SNARKs that are based on this original paper, you do need a trusted setup. And so there are other types of zero-knowledge proofs, Sapling and Pinocchio, that also do this. Also, need a setup. But there are other types of zero-knowledge proofs that don't need the setup. For example, ZKSNARKs. But if we stick with ZKSNARKs, people have gone on from that, and there's a lot of research been done in the last year. Sorry, this slide was from a talk I gave in Paris just before the lockdown started. It's on YouTube if you want to watch it. And there was, and also on that at the conference, Zach Williamson from Aztec was doing a talk about ZKSNARKs. So that's also available on YouTube if you want to have a look at that. But they have taken the original idea behind SNARKs and tried to improve upon this, particularly this project Sonic. And the idea behind these types of SNARKs is, yes, they do still require a trusted setup, but once you have done this setup, you can modify it to some extent. So if what you're trying to prove has changed, it may be the case that you can still use the same setup in producing a new proof, and you don't necessarily have to go through the whole setup again. Now, this is not to say that you have to go through this setup if you're trying to produce a proof of a different witness. So if we go back to the idea of Peggy having her proof, so if the thing you're trying to prove is, say, something about the color of a billiard ball, then you would have to have a trusted setup that involves an algorithm that shows how you would prove knowledge of that. But you could do this, you could create multiple proofs along with that, with different secrets for each proof. So you wouldn't have to go through the setup again each time, unless you did a different, unless you were trying to prove a different thing, unless the algorithm that you used was in fact different. And what Sonic allows is that you can actually change what you're trying to prove within certain bounds without having to go through the whole setup again. And if you look at some of the current areas of research in zero-knowledge proofs, these are some of them. There are improvements on the way SNARKs are being done. So, for example, doing ideas around trusted setups or some of the cryptographic primitives in there. There are things called recursive SNARKs, and I'll talk about those in a second. Alternatives to SNARKs. So this is the idea of other zero-knowledge proofs that don't require a trusted setup, such as STARKs. And then also, there's a lot of research going into post-quantum cryptography. So again, this is an area that doesn't just apply to zero-knowledge proofs, but it also is important for blockchain, but also it's important outside blockchain. But of course, I'll skip through the improvements to the cryptographic improvements. There's more detail than we really need to go into. Recursive SNARKs. I'll mention this because I'm giving a talk tomorrow. If you're interested in this, about recursive SNARKs. So there is a project called MENA, which uses recursive SNARKs to produce a succinct blockchain. And there are some links there to other areas around recursive SNARKs. But the idea that MENA has, and why this is important for blockchains, is that a typical blockchain, Ethereum, for example, if you want to store an archive node, you will need about 4 terabytes of data. All the data on the Ethereum blockchain as a whole comes to about 4 terabytes. So it's becoming less practical for people to maintain archive nodes. It's less in Bitcoin, but it is still considerable. The idea behind MENA and the use of recursive SNARKs in a blockchain is that what a blockchain is doing in essence is doing a computation, and this computation is proving that a block is correct, that is proving the correctness of the signatures and the transactions and the hashes in that blockchain, and that the blocks are building on each other. So at any one time, you will have accepted one particular block, and a new block comes along, and you will do computation to prove that that block is valid and fits on top of the blocks that you've already validated. And so the idea behind MENA is that you replace this computation with a zero knowledge proof, in particular with a recursive SNARK. So you'll create a zero knowledge proof that a particular block and is correct, which includes effectively includes a proof of a previous block, but that block is being proved also via a SNARK. So this is how the recursion builds up. If you approach it from the other end, so if you started with the Genesis block, you would prove that that is correct by doing one SNARK. And then when you add a new block, you create a new proof that the previous zero knowledge proof is correct. And then that new proof also includes the proof that the next block is correct. And so that proof is a proof of block number 1 and block 0. So now you have just one proof that represents the whole blockchain. And then when you want to prove block 2, you do the same thing again. You create a proof that block 1 was correct and also that block 2 is correct. And then that proof stands for the whole chain. And so this recursive effort means that your blockchain is very succinct, and is the chain itself of this effectively chain of proofs of computation comes to just a few kilobytes. So that's really all you need to store if you want to validate the whole blockchain. And it stays a succinct proof no matter how big the size of the blockchain. And indeed, one of the really magical things I think about zero knowledge proofs is that we can get impossibly large computations proved succinctly. So there are examples people talk about that if you had a computation that might take thousands of years to do, we could produce a SNARK, a zero knowledge proof SNARK, that computation is correct. And that SNARK could just be a few hundred kilobytes in size, and the verification of that could take a matter of milliseconds, even though the original computation that you're proving took 1,000 years to compute. So it does seem magical, but it really is possible. Okay, and as I say, I'm giving a talk about this tomorrow. In this meetup group, if anybody's interested, I can give a link to that. But that goes into more details about recursive SNARKs, and particularly about the MENA protocol. Okay, sorry, some more details about MENA. And link, yeah. Okay. Distributed processing is also possible. So there's a project called DISIC, which takes this the idea of creating the proofs and distributes that, and distributes the computation of that, just to make the whole process more efficient. Okay. What time have we got? Okay, so shall we? So we're coming to where I want to talk about different types of zero knowledge proofs. Maybe it's a good point to take a 5-minute break. Also gives you a chance to ask questions. Does anybody have questions so far? Because I'm going to go now into different types of zero knowledge proofs and then go into more details about the mathematics behind the proofs. So yeah, a good idea, a good time for questions. Okay, well, if we take a break, say till 18:30, and you can ask me questions during that time anyway. Otherwise, yeah, I'll start again at 12:30. I don't have a certificate, I'm afraid. Yeah, it would be nice. I think, I don't know, maybe we should create an NFT or something for people, people who've attended. That would be good. I don't know, Brandon, should we have a blockchain society, a Blockstock NFT for people who've attended? I don't know.
Yeah, that's quite a nice idea, actually. So you mean like a token, like an NFT?
Yeah. So this, there's people would gain. So it's non-fungible, and it would show that people attended the 4-day course, or whatever you really want to use it for.
Yeah, I like that. I really like that idea, actually.
Okay. In which case, if people want to, if you're interested in that, send me your wallet address on Ethereum, and I'll create a token and send them out to people who attended. Yeah, I can do that.
Oh, that is so cool, Laurence. Great idea.
Yeah. If you'd like to have a think of what you would like, want the token to look like. I mean, sort of more details about it, and yeah. But if you send me if you send me your wallet address, then we can send those out once it's been built. Yeah.
I have to say, Laurence, so far the zero knowledge proofs, like I remember hearing about them and I couldn't believe that they were real.
Yeah.
And it's nice to hear that you felt the same way and often still do at the moment.
I do, yeah. It is just, yeah, it really is amazing. I think Vitalik called it, moon math. It just seems amazing that it could be true, but it is, and yeah. And one thing, one reason I chose to speak about them today as well is that the excitement about this area and this sort of explosion in interest and in research in this area is very similar to what it felt like maybe 5 years ago on blockchain, where there was lots of things to be researched and lots of things to be found, and it was just hugely exciting that it seemed that every day something new will be happening. And I went to a conference about a year ago, and people were complaining that there was so much happening they just couldn't keep up with what was happening. So every day there would be something new happening in this area. So yeah, that's one of the reasons I love it, and I would really recommend it to anybody to get involved. Use it in blockchain, or to get involved in research in this area, because it's amazing, fast moving, and hugely interesting.
Yeah, I've got so much catching up to do. I mean, it's like, oh my gosh. I mean, because I mean, imagine coming up with this idea, zero knowledge proofs, and someone just says to you, yeah, but come on, I mean, like, you're dreaming, you must be absolutely bonkers, and it's
and I mean, I don't think I've got the slides here with their history actually, but I mean, they were really first invented in the 80s, and it was Silvio Micali who wrote the original paper along with others, Carl Wasser, etc. But he wrote this paper, and I think for a while it was not really taken up by people because people just didn't get it, and it took a while for people to, I think, really understand the potential, and just how. The potential of the area and just how revolutionary it was. And then also it's interesting because he then went on, he's been a giant really in cryptography, and he went on to found Algorand, and he's been very involved in the blockchain space since then. So a real giant.
Yeah. Mm-hmm. Well, times are changing, eh?
Yeah.
The one thing I don't know is when What does the NF stand for in the the NF?
Oh, non-fungible.
Non-fungible. Okay.
Yeah, so with Bitcoin or Ether, you can split it into smaller denominations and spend those independently. You can spend 1 Satoshi. With an NFT, it's indivisible. It's just one thing. So you can transfer it to somebody else, but just as one thing. You can't transfer half of it to somebody else. Yeah.
Okay. Yeah, that's really cool. Oh, that is such a cool way to get a certificate. I mean, it makes so much sense, right? Like the blockchain society or Xtree.io sends out NF tokens versus, oh, well done for participating in this Coursera course. Here is your certificate you can add to your LinkedIn. It's like, yeah, well, this is on the blockchain. It is immutable. Beat that.
Yeah. It's real proof.
Stamped, signed, and sealed and delivered. The whole 9 yards.
Okay, shall we carry on then? I mean, I do. There's not been questions. I do appreciate that it is. Yeah, it's quite a daunting area when you first see it. So you'll probably take you a while to think and get your head around a lot of these things. So, but please, yeah, if you have questions, I'm happy to answer them. If you want to email me afterwards, and hopefully one day when the lockdown ends, we can get back to doing workshops, because we used to do a weekend workshop about zero knowledge proofs and do sort of mini hackathons as well. So hopefully one day soon we'll be able to get back to that. Anyway, to continue. So I spoke about ZKSNARKs and how they have this trusted setup, which is seen really as a disadvantage. So people have tried to do zero knowledge proofs without that. The main sort of alternative is a Stark. And there is a company called Starkware who are very much involved in pushing the research in this area, but also commercially and producing products. And yeah, if you're interested in DeFi or blockchain optimization, I really would check out. Starkware. They're doing some great things, some really interesting stuff. Oh, so your question. You missed the certificate or not? Yeah, what I said was we'll put together a non-fungible token. So if people want to send to me or to Brandon, probably is better, your wallet address, then we'll put together a token on the Ethereum blockchain and then give you an NFT token to prove that you participated. So yeah, we'll do it that way because we don't have a certificate yet. Okay, so Starks, yeah, so there are different type of zero knowledge proof. They completely different way of working. They have a much simpler setup. They don't require this trusted setup and this big computation. All that has to happen is that the prover and the verifier agree on a hashing algorithm, effectively. They're much simpler. And yeah, I won't go through much of the details for that. They also seen as being more scalable. Yeah, as you can see here, with the complexity of what you're trying to prove. Similar things, bulletproofs, they're very much about proving that something lies within a range. So, for example, if you want to prove that your age is between 18 and 25, bulletproofs are very much about that. But they're a different type of zero knowledge proof, different from SNARKs and STARKs. And there are different projects that have been set up around these. Some links there if you want to read up more about them. This diagram, very useful. I got it from, there's a very good blog post that I got it from, that is a little bit old, but it gives you an idea of some of the trade-offs between different types of zero knowledge proofs. So for the SNARK, for example, the complexity size is a constant, but you do require a trusted setup. For STARKs and bulletproofs, the size of the proofs and and the verification cost is can be higher. But for example, you don't need a trusted setup, and SNARKs in particular are post-quantum secure. So if quantum computers come along and they break some of the assumptions we have in cryptography that underlie SNARKs, SNARKs will still work. So they're good from that point of view. Okay, yeah, I won't talk about that really. There's an area of cryptography called lattice-based cryptography, which is popular and is being used by people. But yeah, I won't go into that in any more detail. I will go into a little bit now about the real detail of ZK-SNARK. So I want to do this really to give you a flavor of what happens in a ZK-SNARK. So, so far, what I've done is some very hand-wavy, intuitive idea of what a SNARK is and what this zero knowledge proof is, without showing you how it's done. Now, we don't have time to go into all of the maths, so I am still going to have to make it rather general and be a little bit vague about some of it, but I want to give you a flavor of what is involved at least, because I think that can be useful. And you can also then go into, you know, there are plenty of resources where you can go into it in more detail if you're interested. Okay. Actually, when we did our workshops, we have some resources for this. So we put together a maths primer, because some of the maths involved is not the kind of maths that people do really at school. It's not necessarily that much harder. It's just things that people don't generally do at school, things like group theory. All of this is explained in more detail in some of our blog posts and in some of our resources. So you please feel free to use those resources. But when we create a zero knowledge proof, and when we create a ZK-SNARK, what effectively we're doing is we're transforming our problem from one form into another. And what we're transforming from is really like a small program. So when I spoke about Socrates initially, what you can do is you can write your proof as a small program. And what happens when you create a ZK-SNARK is that you take that and then you transform it mathematically through a number of steps into this final result, which is a ZK-SNARK, which really looks just like, it's just a piece of data. It just looks like a large number, but that is an encapsulation of the original program that you created. And just to give you a flavor of what it is that you may be using for your proof. Imagine you were doing something very simple. Maybe you had some simple mathematical equation, and you just wanted to prove that you knew a value that made this equation true. So it could be that the equation is x squared equals 4, and you wanted to prove that you knew the value for x for which that is true. Okay, obviously, a very simple thing. You all know the answer, but you could generalize this and make this really any kind of mathematical equation. So the idea is we would take some program, some computation, and we want to represent that thing shows whether we have knowledge of this secret or not. So if you had that, if you were looking at that example, in our computation, we could take the secret that we input. So say I input the secret 2, which is my answer. So I'm claiming I know the answer to this, and I input this secret 2. Then our program could just square the input that we did. So we'll square 2, we'll get the answer 4. We would compare this to the answer that we require, which is also 4, and we'll say, yes, they match. Therefore, this has been proved. This person does, in fact, know the solution to this equation. So it could be something as simple as that. But this computation really has to show whether you do know the secret or not. But that computation, obviously, if we can't just pass that between the prover and the verifier, because the prover would then have to give the verifier their secret, which we don't want them to do. So we have to go through a number of stages. And these are the stages that we have to go through. I'm not going to explain all of them. In fact, I'm just going to go through the first few. They're all different types of proof. But they are, I don't know if there are any mathematicians or computer scientists, this is very similar to the ideas in complexity theory, where you're doing transformations between kind of equivalent problems and showing that these problems are mathematically equivalent, and you can transform them from one form into another. And that is what we essentially are doing when we create a ZK-SNARK. We start off with some simple algorithm, and then we transform it through many, many stages into this eventual ZK-SNARK, which then fulfills the properties that we had to begin with, that it is a complete proof, that it is a sound proof, and that it has this advantage of zero knowledge. Okay, now one thing we need to know about this, one fact that we use throughout this, is around polynomials. So I think everyone will probably know what a polynomial is and understand a polynomial, that it is, it's an equation built up of powers of some variable x. And there is this lemma about polynomials, which we really rely on, and the fact that if two polynomials are different, then they will be different at most points. And so a lot of the computation we do really relies on this in our zero knowledge proof. When we're trying to prove that we know something, what we end up doing is really showing that that some polynomials are matching. And we know from this, because of this lemma, that if the polynomials didn't match, then any point that we chose to evaluate these polynomials would come out with different results. So it would be very difficult for us to have two polynomials that are different that actually agreed when we evaluated them at a particular point. So as we'll say later on, what we try to do is we try to make some calculations at different points. And the verifier is doing this and the prover is doing this. We're calculating values at different points. And we're saying that if what the prover is doing is correct, if this is what the verifier is expecting, then these calculations at these points will come up with the same result. Okay. The other technique that we rely on is called homomorphic hiding. And this, again, this seems like magic to me, but it also is a way that we can even make this process of calculating our polynomials even more robust, because we wouldn't want the fact that maybe if our prover knew that we were going to make our calculation at a particular point, say at the point 10 and 20, maybe they would change their polynomial so that it would match up with what was expected at these points. So if they hadn't some knowledge of what was expected in terms of which points were being used, maybe they could cheat somehow. And so there is also this additional thing, homomorphic hiding, which is done to kind of obfuscate and prevent them from cheating and kind of fooling the verifier by the results that they get. Again, I don't have time to go into this, but I do give you some links into some blogs that go into that in much more detail and explain it quite well. But the first thing we do is we take an algorithm, we do this thing called flattening the code, and then we take this and turn this into a thing called a constraint system. Once we have a constraint system called a rank 1 constraint system, or R1CS, we then turn that into a quadratic arithmetic program. So yeah, we love our jargon here. So these are the first few steps we go through. So we're starting with a program written in some code. We're taking it into a constraint system. We take that into what's called a QAP, and then at that point we effectively have some polynomials, and we can start to do our magic with polynomials and try to do our matching. the flattening the code, this code is the kind of thing that you would, if you use Socrates to create your proof, this is the kind of code you could write. So you would write a function like this. It looks a bit like Python, but you would have some function, and this is effectively evaluating x cubed plus x plus 5 plus, yeah, x cubed plus x plus 5. Yeah, so a polynomial in x that you input. So that could be our input algorithm, and we're trying to prove that we know, say, a value of x that equates to a particular answer for that. When we say we flatten it, what we do is we take all of the potential intermediate steps as intermediate variables. So we end up with lots more variables than we initially had. We also take out any loops in the program. So if we wanted to loop through something 10 times, we effectively have to have 10 steps in our flattened code. So you will start to see that this is one of the reasons why zero-knowledge proofs are difficult or have problems with scalability, because we're trading time for space here. Really, we're taking out these loops in time, and because we're flattening them out into space and variables, so we have them kind of all at once. And from that we constraint system. Now this often puzzles people. People get the wrong idea about this. So this rank 1 constraint system is not a computer program in the sense that people usually understand them, in the sense it's an algorithm that goes step by step. What it is creating a system which has various variables and sub-circuits. Now I'll show you a little diagram of one which will make more sense in a second. But it has all of these parts, and it really says that these parts are all constraints upon our values. That mean that if one of the values we put into the system is our secret, then the constraints taken as a whole in our system will constrain the system to be true if that secret is the correct secret, or false otherwise. So it's not like as I say, a program that goes step by step through something. It's really a system of constraints. And people who write zero-knowledge proofs sometimes understand these so well. I mean, there are people in the Zcash team who can start with these constraint systems and write them by hand rather than starting from a higher level program. But they are difficult to write unless you know what you're doing. They look like this, really. And even though I've got arrows on them, they do represent sub-circuits, and they do represent kind of equations in there, but they really do think of them as being constraints on how you put something together. So here we're showing we have an expression so that we want to prove that we know a value, or we know 3 values, such that when we combine these in a certain way, we get an answer 7. And so we have some inputs into our constraint system, C1, C2, C3, that we're saying that we know, we want to prove that we know. And the output of this little circuit is the constraint on that is that it is 7. And this whole thing has effectively these weights and these gates. So you're seeing multiplications and additions here in these little sub-circuits. And the whole thing is very much like a hardware circuit that is being put together. But if you get all of these constraints correct, then the whole system will evaluate to true, and that will prove that you knew the input. So we've taken our original algorithm and we've reduced it to this system where we have a number of constraints and a number of inputs. So this is how we've taken our original algorithm and ended up with some constraints, some inputs, just some numbers. And then we can use these numbers to build up our polynomials. So the next step is to go from that circuit into our polynomial. And I should say all of this, if you use Socrates, all of this is done for you. You don't have to do this by hand, but obviously this is what is happening behind the scenes. And somebody, when they did the research to this, they obviously had to prove this and work out how to do this, which is, to my mind, just amazing that they could manage to do this and think of how to do this. But anyway, so there we had our circuit with these constraints, with these inputs, and then from that we then build a set of polynomials, and they are given certain names. So they're called left, right, output, and H. Again, I'm not going to go into what these represent. There is a great blog. So Alex writes this blog, Code as Errand. He explains this and all sorts of stuff to do with blockchain really well. I really recommend his blog to anyone. It's well worth a read. But anyway, we've got our system. We've transformed this into a set of polynomials, which is our quadratic arithmetic program. And then we want to start evaluating polynomials at various points. So I must apologize here, actually. I've said Alice and Bob. I really should have stuck with Peggy and Victor. But here, Alice is the prover, Bob is the verifier, and we're going through. So Bob is going to start saying, okay, you've got these polynomials. I know what I want these polynomials, what I expect from these polynomials at various points. So I'm going to start to pick random points, and I'm going to expect these polynomials to behave in certain ways. But again, there is this hiding aspect going on because we don't want either Alice or Bob to have too much information because then they could cheat and they would end up with more information than we would want them. So there is this extra complex process involved with hiding how these things are evaluated. Again, I'm not going to go into that anymore. It requires some cryptographic assumptions to do this, but it all works, and the end result, is that at the end of it, Bob will see that these polynomials match what he is expecting at some random points that have been chosen. He can then use this idea that if the polynomials were different, they would not match at the points that he has chosen, and so therefore he can assume that these polynomials are the same, and then from that, he can assume that Alice or Peggy, who produced these polynomials, really had the correct values in the constraint system, really then had the correct inputs to the program that mean that she really did know this secret value that she was trying to prove. So I do apologize to the mathematicians that I've gone through that in a really vague, informal way, and probably said a lot of incorrect things, but I wanted to give people just a flavor of what is involved in producing this type of zero knowledge proof. As I say, this is how a ZK-SNARK works. It's not how a SNARK works. They are done differently, but this is one way to do zero knowledge proofs. If you have questions, please ask. I've probably presented so much there, it's difficult to know what to ask, but I'm happy to have a go.
Yeah, any questions, please fire away. Try and pick Lawrence's brain as much as possible. It's hard to come by people like Laurence, I can tell you that. So
we do have more resources about these, so please follow the links. There's plenty of good blogs as well, or you can also email me questions if you have them. Okay, so we'll look at some of the use cases. And one thing I found, I mean, I love zero knowledge proofs, and I would love to put them, have projects built around them. But there are some difficulties when trying to do this in the real world. Often we come across the problem that of public data, that maybe the prover and the verifier have some input to this thing they're trying to prove. that is public data or that they share. And so we sometimes come to the idea of how can these two people trust that their sources of data are correct. And so you often end up, if you're trying to do this in the real world, you often then end up looking at things like oracles, or maybe a blockchain could be a source of data for these. So we do sometimes get blockchains involved in helping with the zero knowledge proof itself. One of the easiest ones, or the first ones where this happened, is in cryptocurrencies. So the first one, Zcash. So that when we talked about Bitcoin, we said, for transparency, it's a public blockchain. For transparency, we want to be able to show when we've done a transaction that transaction is valid. But that does mean that everybody in the world can see who initiated the transaction, how many coins they sent, and who those coins were sent to. So Zcash is the idea that we can somehow hide that. Now Zcash operates in two modes. You can make transactions where the transaction is transparent, so the way you don't hide the details, but you can also do shielded transactions where people cannot see get the details about the participants in that transaction. And in particular, what they're doing really, what the zero knowledge proof is doing is proving that this transaction was correct, but without giving out details of the people involved in that transaction. So that was one of the first applications that I came across of zero knowledge proofs. And other people have done similar things. So there are other cryptocurrencies around. So there's Grin, based on a technology called Mimblewimble. And if you've been following the news, it was just a few days ago, I think, when Grin was attacked. Somebody did a 51% attack on it. Yeah, it's a great shame. It's a very interesting technology, well worth looking at. Monero, also another privacy preserving coin. They went through some different stages, I think. So initially, they were not, I don't think initially they were using zero knowledge proofs, and then they moved over. I think they're using Bulletproofs now. But anyways, cryptocurrencies, a good use case for zero knowledge proofs, quite a simple one to do. Yeah, there's some details there of how Zcash works. One of the ideas behind it is that you have these things called notes, which are showing the spend that it is really based on Bitcoin. So there's still this kind of UTXO model, and notes are used to prove the ability to spend, transactions. But these are done, these are encrypted, but then also we have these things called nullifiers that are used to show when these things have been spent and these notes have been used. But it is all done in a shielded way, and hashing is done. There's kind of commit reveals done to shield the details of these transactions from people in the system, so that you really can preserve your privacy with Zcash. Yeah, I won't go into more details about that, but a great use case. Successful. Zcash has been around for quite a few years. Actually, on one note, that they did their initial trusted setup, and they based their system on a research paper, and unfortunately, this paper, there was a mistake, which they then copied this mistake into their implementation, and then some members of Zcash, after the system went live, they were working on the stage 2, version 2 of their system, and they suddenly realized that there was this fundamental flaw in version 1, which meant that someone could, if they could potentially mint free tokens, and it would never be, it could be done without being visible to the system. It could be done kind of secretly, and you wouldn't be seen caught by the system. So they kept that secret, and then brought out their second version to fix this. And luckily, they think that nobody exploited this in the first version for other reasons. They had other reasons to think that they would have perhaps caught this, other than the aspect that they that's used to prove the transaction. But it was very lucky, because that could have really wrecked the whole thing. Done that, it could have meant that somebody would have been able to just mint their own Zcash without really. They could have done their own invalid transactions without it ever being flagged. Yeah. Anyway, so one of the use cases, another use case is scalability. Now, this really is relying not so much on privacy, the privacy aspects of zero-knowledge proofs, but more the proof aspect and the fact that you can get a proof of a computation and represent it in a very succinct form. Because the scalability problems, so I've already mentioned the amount of storage needed, but also things like throughput of transactions is problematic for Bitcoin and Ethereum. So people have come up with schemes to get around this. There's the idea of roll-ups. So a quote there from Vitalik Buterin. So the idea being that you can get transactions, so you can roll them up into a single transaction. So this decreases the amount of transactions that have to be checked in the system, but that you produce a ZK-SNARK of the validity of all of these transactions. So then you have one proof that you're putting onto the system that can then be used to prove that all of the transactions in this particular roll-up were correct. And yeah, the whole thing is obviously much quicker and can improve the throughput of your system. Something that's come out very recently from Starkware, again, yeah, I really do recommend people to look into this project more, is the idea, again, so this is using SNARKS, not ZK-SNARKs, but the idea of a platform of proofs for general computation. It started off with kind of a hackathon, I think, and it's now this complete system. And they claim, their amazing claim that they managed 300,000 transactions into a single proof. So if you think about the problems we have with blockchain scalability, it's really obvious that these kind of approaches have tremendous potential to help. Okay, that's scalability. Other ones, there are some really interesting use cases. One I came across is to do with nuclear weapons and verification that these are being dismantled. And I think it is perhaps, it really goes without saying that countries will want to keep details about their nuclear weapons secret. These slides, by the way, I got from, these are from Los Alamos, and this is the project that they did to prove that they are in compliance with treaties. And the idea being that they can prove that they've dismantled various nuclear weapons. And they do it, there's a mixture of technologies involved. And again, I say, I took this slide from them. I don't know what Darth Vader is meant to represent here, really. But anyway, so they have a number of technologies. So some of it's AI, they have a neural network, and this network is proving details of their nuclear weapons. And so that what their proof is doing is proving a number of things. It's proving that this neural network is doing the computation correctly. So whatever that network is doing, and I don't know enough about how they prove the weapons have been dismantled to know what that thing is doing, but the proof is proving that it is doing the computation correctly. And then it's also proving inputs to the network that they are correct, and sort of wrapping all of those up in a proof or a number of proofs, and then sending those proofs to a verifier who then can put this proof through some verification software, and that will come back with a yes or a no and say, yes, they have complied with this treaty, or no, they haven't complied. And because they've they've shared the details of how this system has been built and the things they're trying to prove. Each side can be confident that they're not being cheated here. So quite an amazing use case. I hope you'll agree. The fact that you can do something as vital, I guess, or as dangerous as nuclear weapons by some simple mathematical proofs. It's amazing. Something perhaps more down to earth. There is a lab at Edinburgh Napier University called the BlockPass Identity Lab. So BlockPass, a company who are working in identity, and they are using zero-knowledge proofs around identity. So this great use cases around identity. I often feel when I'm going to restaurants or coffee shops where they ask for my name, I hate having to tell people that. I hate the idea that I'm leaking my information when they don't really need it. I would love to have my identity say on the blockchain, but in a secure way, and maybe in a way that I could selectively allow people access to items about my identity. So maybe I would want to prove that I'm over 18, but I would not want to give away my exact age. Or maybe I would want to prove that I have a certain address or that I'm allowed to vote, but not to give away details about that. So I think this is a great use case, the idea of zero-knowledge proofs built around identity, where you can just give a simple proof of whatever it is that your identity allows without giving out any other information about your identity. So yeah, I think it's a great use case. Okay, that's I think all of the use cases I have on zero-knowledge proofs. So really that ends the part about zero-knowledge proofs. Does anybody have any questions around that before I go on? Okay, thank you. So I'll go on now to just briefly mention something that somebody asked for last week, which was formal methods. And I've not looked into this a great deal. We've done a little bit of work. One of my colleagues did a little bit of work with formal methods, but I can't go into much detail about this. I don't know it in much depth, but I certainly know a little bit about the history of or the need for it, because back in 2016, there was a project called the DAO, which was it was a decentralized autonomous organization. It was a smart contract that was allowed to do funding of projects. It was massively subscribed. So I took this screenshot when they've just finished their funding, and you can see on the left-hand side, they effectively had $220 million worth of Ether tied up in a smart contract. So a real honeypot for hackers. But this smart contract had total control over this Ether, over this cryptocurrency. And the inevitable happened a few weeks later. I got up and suddenly all over social media, I saw messages like this. I'd never seen anybody say this is not a drill before in real life. I've seen it in films, but not in real life. But people were saying that. And somebody had started to drain the Ether out of the DAO contract. It was a slow process. It had been going on for a number of hours. I think there's a few $1 million worth of Ether had been drained when I saw it. I should say, I think this would make a great film. So if there are any filmmakers out there, I'm always trying to persuade people to make a film out of this. I also have a talk about this if people are interested. It was a really interesting, the way it happened was really interesting, and the fact that it went at a reasonably slow pace made it an exciting thing to observe, and meant that people could get quite involved with it. But yeah, that's by the by. But anyway, important thing for this formal methods is the fact that there was a smart contract that was not behaving as expected, and that somebody was using it, was taking advantage of it, and was draining millions of dollars worth from this contract, and that the people who had deployed the contract couldn't do anything about it. So they had put the contract out there, and it was autonomous. They had no means of changing the contract or changing what he was doing. So the world really was sort of sitting back and thinking they were going to lose all of the ether. I won't go into what happened. It was a very interesting story. Yeah, please read up on it. But it did lead to people being much more aware of the vulnerabilities of contracts and the cost of smart contracts going wrong, or of smart contracts not doing what you expect them to do. And so not long afterwards, the Ethereum project hired an engineer to look into formal verification and to advance this field, and other people did as well. So I know Microsoft got involved. A lot of people got involved in research in this area, trying to show that a smart contract or that Solidity would behave in a certain way, or to formally prove that the contract could not get into a certain state. So that was really the motivation behind it. That was a few years ago, and the field has developed. I mean, formal verification generally is a very difficult area, and it's very difficult to prove languages are formally correct, or formally prove that languages are correct. There is a very good overview, so there's a link there to an overview of the current state and all the projects that are involved in this. The one that we were involved with slightly was using the K framework, which is a framework that has been used in other areas of computer science for verification. They've produced a specification of the Ethereum virtual machine, so the semantics around that, so to be able to prove that. And we used it at one point to do a little bit of verification around the ERC20 contracts and to formally prove that functions in an ERC20 contract were behaving as expected and could not get into a certain state. There are other approaches as well. SMT checkers as well have been built for Solidity. There are a number of papers. I can't remember which one. I think one of these. There's some people in Oxford researching this as well. I think generally formal methods are an area of research generally in computer science at Oxford. But yeah, there's there is a sort of a body that's been set up in University College. I forgot the name, but it's I can't remember how it's called, Blockchain Institute of University College, something like this. But it's Bill Roscoe, Professor Roscoe, who set this up, and he's doing some research into this area as well. So if you're interested in researching into this area, go have a look at that. But I would have a look at this overview, because there's some great links there to areas if you either want to use this, or whether if you're interested in research in that area. Yeah, there's plenty going on. And even if you're not doing it very formally, there are also lots of projects that do static analysis of Solidity, a static analysis of contracts, even if it's not quite formally verifying it. I would recommend everybody to use all those tools as much as you can. Okay, so that's all I wanted to say about formal methods. I'll just quickly say a little bit about some other resources you might want to use. We've already mentioned the resources we have on our foundation website. We've put together all of our educational work on there. We're firm believers in community education. We love to do it. As I said, before the lockdown, we were doing workshops pretty much every weekend, and community education workshops, these were all for free for developers. We covered blockchain in general, all aspects of developing on blockchain, and also zero-knowledge proofs. So in the hope that we will soon be out of lockdown and we can restart these, I hope we'll be able to see some of you go to those. I'll come to some of those we will do again. But anyway, we have our website for that now online. There's lots of hackathons going on at the moment. Obviously, the one I think you've already heard about. And thank you for the people who came to this rather than going to the introduction to this hackathon, which is on at the same time. But I'll still talk about this. There's a hackathon at the moment from Encode Club. I think everybody knows Anthony from there as well. So this is finishing in January. There's some great projects that are done in this hackathon. So if you've got any ideas you want to try out, or if you just love hacking, yeah, I really would recommend going along to this. If I'm going to give a talk on Monday for the people in the hackathon, so I'm going to go through the introduction to blockchain again. So if you missed that and want to hear it again, I'll be doing that. But yeah, you can sign up to that still. But it's already started. I mean, people have already started hacking, I think, but I think you can still sign up for that. If you're interested in research, there is the Ethereum research site. If you're interested in that, so some really, obviously that's the top people there. You're working on the Ethereum blockchain. So a lot of people doing some interesting areas in cryptography and zero knowledge proofs. As you can see, they're doing stuff on rollups, all of the stuff around the transition to ETH2. Yeah, so there's their website. So yeah, go check that out if you want to get involved in that research. There's also lots of bounty programs. I mean, this is the Ethereum bounty program, but a lot of, I would say the majority of blockchain projects have bounty programs. So it's a great way to investigate, learn more about blockchain, learn more about specific projects, but also to get if you're interested in working in these areas, to get your name known to the people in these projects. And it's very common for, particularly among open source blockchain projects, for people who have contributed from the community to then be asked to take part or work for the projects themselves. So if you're interested, you want a career in these areas, getting involved in these types of programs is a great way to start. Okay, so that's everything. If I'll just go back to our foundation site to give you. I've finished quite early. There's plenty of time for questions. I hopefully haven't baffled you all. As I say, I'm happy to take questions now, or you can email them to me later. But yeah, that's the end of things so far. So if you have questions, yeah, I'm happy to answer them.
Any questions? I mean, that was amazing. But any questions before I start rambling away?
Please, please ramble.
But yeah, great reminder on the hackathon. So there's the Encode Club hackathon, which officially starts today. At least as a launch event. There is also the Oxford Hack, I think, which is this weekend. If anyone's interested in doing that, it might be a bit late to register, but who knows? And I think definitely take up the educational resources that Laurence has provided, including the blog and what's the guy's name? Alex Pinto. Which I'll link as well in the YouTube video description and on the Medium. But I guess one thing I had, because you mentioned Grin and Mimblewimble, and I saw recently that I think it's Litecoin, they put up a testnet, I think, from Mimblewimble. They had a few bugs. And like, how does something like that change the system? Like, will it be a massive, almost like paradigm shift where, if Litecoin can do it and then Bitcoin can do it, then everything becomes anonymous. You know, you don't have the pseudo anonymity present with just changing addresses.
Yeah, I don't know. I thought when Zcash came out, I thought there would be a massive rush for people to use that for private transactions. But I haven't looked in the last year, but about a year ago I looked at it. I think 90% of the transactions on Zcash were not shielded, so people were not taking advantage of the anonymity there. So I guess it depends on people how much they want the anonymity of these coins, whether they're happy for the fact that people do forensics, for example, on the Bitcoin blockchain. Your anonymity is really only pseudo anonymity, and certainly, I suppose if people, it's widespread adoption and people invest more and then realize that the centralized exchanges, when they did their KYC, those exchanges are then passing those details on to the tax authorities, who then will start to say, well, you have got this wallet and we saw you've made some profit on your Bitcoin, so you owe some tax. Maybe that will incentivize people to go for the privacy preserving coins. I don't know. It's an interesting point. Yeah.
That's interesting, because I had no idea that still, even on Zcash, people haven't almost flipped the switch and said everything private.
Yeah.
Okay. Yeah, because I guess the tax situation for cryptocurrencies is a bit difficult at the moment, where for last time I checked, I think if you make any purchase, at least in the UK, you need to realize your gain. So even if it's for a good or a service, buying a cup of coffee, you need to calculate the gains you got when you bought Bitcoin or whatever cryptocurrency, and then when you bought the cup of coffee. So it makes it kind of difficult to manage.
Yeah. And there are some good accounting packages for that. Just say there's one, I always forget the name of it. It's a guy based in Berlin who's got a package, accounting package, like I think it's a open source software that helps you do all the accounting for all of your cryptocurrencies. I'm sorry, I forgot the name of it, but
yeah. Because I think that's going to be really important when we have people like, PayPal saying, oh, go ahead, start buying and selling, cryptocurrencies on our platform. At the click of a button, and they have like 300 million customers or something crazy like that. Are all 300 million going to be declaring their gains and losses in the appropriate way? And will we see that almost put pressure on the regulators in a sense, where it's almost the masses, there are so many people doing it, they're like, oh, okay. Or will realistically that PayPal might use something like that, a built-in software package.
Yeah, I just found the name.
Awesome.
It's called Rotkey.com.
Rotkey.com.
Yeah.
Awesome. Yeah. Oh, so.
And working on bus carrier or selling tickets. No, I don't. I don't know of that. I know I spoke to one of our clients I spoke to about something a little similar to this, the idea of using something to, so you could have, it's like a contactless idea on buses, and you could use cryptocurrencies on them. But I don't know anybody that's doing anything quite like that. No, sorry.
I mean, the thing is that's quite an interesting point. Like, the using cryptocurrency on transport systems, where, I mean, you know, is a block mining time issue, or, you know, will people just have faith that no one will try and do a double spend? Because I mean, surely the probability of that happening is getting slimmer and slimmer as the chain gets longer and longer.
Yeah, yeah. I think you have to just, they would have to take the transaction and yeah, they can, you could, whatever is taking your transaction could can validate that it looks correct and just hope there's no double spend. Because I mean, Bitcoin, you don't want to wait 10 minutes to before you can get on your train or whatever bus.
Yeah. Because I mean, because then, okay, let's say you get one confirmation, you know, the likelihood of that being reversed is pretty low. And then once you have two, it's almost like an exponential fall off.
Yeah.
And I hear like 6 is normally good to go, you know?
Yeah.
I
think it depends on what you're using it for. So if you're buying a coffee, then okay, maybe you would if it goes wrong, okay, you lose the price of a coffee, but that's probably not so bad. Whereas if you're buying a car, then you would want to wait 6 confirmations. So yeah.
Oh yeah, also Laurence, it'd be great if you popped the if you have it, but the MENA meetup you mentioned, I think. Or if it's in the slides.
Oh yes, I think it's in the slides. Yeah.
Okay.
Yeah.
Awesome.
Yeah.
So I can pick that out because the link to the slides I have, which I'll send out. But other than that, any questions or anything else you wanted to add, Laurence, in terms of education or getting in contact, or more details about XRP and what you guys are working on, or if that's top secret?
No, it's not secret. By accident, we've ended up working on in the automotive sector quite a bit. So we're doing that a little bit at the moment, although there's no real reason that should be the case. That came about because we won a competition to put blockchains in Porsche vehicles a few years ago. But yeah, so we do that. Generally, I think the only thing I would add is, this area is, I really would encourage people to get involved. So I used to work in traditional software development, and it's just been an absolute life changer getting involved in blockchain. And it can be difficult at times. I guess it has its ups and downs, but I've never regretted it for a second. And the projects you can work on, and the research you can do, and the areas you can get involved in, and the people you meet in the community, they're just fantastic. So I can honestly absolutely recommend anyone to get involved at some level, either working in the area or doing research in the area. I really would do encourage you to do that. It's fantastic. I feel very lucky that I've been able to do that.
Yeah, I gotta say, I mean, I think it's amazing, especially just seeing how rapidly things change, because I feel there are two sides to the coin. Excuse the pun, but like you have the general hype media side where everyone's just simply focused on the price, and making a quick buck and seeing it go to the moon, or maybe not that quick, but maybe a long-term investment. But then you also have quietly working away people like you, other blockchain developers who are kind of changing things for the better in terms of trust and consensus. And I mean, when you start to pair that with the way things are moving with the Internet of Things, and you mentioned Porsche, and I remember you demoing your work, and it was just, it's like, wow, almost like updating technology for this automation kind of revolution, where now, you know, you have machines which can muck around with currency essentially, you know, and hold value and share that value.
Yeah, and there's an interesting project going on at the moment, Space Chain, where they're putting the blockchain to space. They've had a transaction from the International Space Station, and they're based just outside. I mean, they've got an office just outside Oxford. Yeah, yeah. There's some very, very interesting projects out there. Yeah, it's not just tokens. Yeah, there's some amazing things happening.
On that note, actually, would you say Oxford is kind of a hotspot for this stuff, or is it mainly Silicon Valley, or is it more of a distributed network across the globe and into outer space?
Yeah, yeah. So Oxford, I thought was fairly slow, and London seemed to be doing. You know, UCL and King's, Imperial had quite a lot. Were doing a lot more. So I wouldn't say Oxford's that good really. And then generally, I mean, London was quite good, but also Berlin had a lot of things happening there. Where else? Yeah, Edinburgh's doing quite a bit of quite a few interesting things. Different areas, yes. I mean, Estonia, they got involved with all sorts of stuff. You know, quite early on, they became a centre. Malta, Gibraltar, especially around tokens. So yeah, it is all over the place. And I think Silicon Valley perhaps didn't develop it as much as you would have expected. I think other areas have not overtaken Silicon Valley, but I don't think they have done as well as they could have. Yeah.
I think we've got a question from Mo Yakubu in the chat.
Yep.
So
yeah. Yeah, I mean, if there is, yeah, I would say if you're interested in DeFi, get involved in hackathons. They're a really good way to try out ideas. There's so many resources. So something we've just published. So last week and this week we did a couple of articles on Medium, and they're also on our website, about how to develop an arbitrage bot on DeFi. So how to write a bot that will sit there and then look at the decentralized exchanges and do arbitrage for you. So that's looking at that and how that works, and the contracts used with that are a good way also to work to find out more about DeFi. It is difficult though. I mean, DeFi is changing so rapidly. It's amazing. The other thing, to mention, podcasts. There's some very good podcasts. There's one called the Zero Knowledge Podcast that I really like. It's not just Zero Knowledge Proofs. It's more generally about blockchain, and they have some great guests on there. So yeah, have a listen to that. But there are other blockchain podcasts as well that do some great work.
yeah, it's true. I mean, I think Tom mentioned a podcast last night as well. It was the original Let's Talk Bitcoin, I think, as well, which is quite a nice little introduction, but also they delve into some heavier stuff. Yeah, I guess we're at 7:30, so I don't wanna hold everyone here hostage. But thanks again, Laurence, for a great talk, a great series of talks. I mean, like, think about where we started. You know, it was that introduction to what a blockchain is, and Bitcoin and Ethereum, and now I guess I was followed by coding in Solidity and Remix, then getting exposed to Ganache and I mean the IPFS. So, and here we are looking at zero knowledge proofs on the frontier of blockchain research. So massive thank you, Laurence, and also pass on our thanks to Tom as well, because
Will do.
it's actually been quite a journey. Like I've been looking back over the Medium post, I'm like, oh my gosh, you know, it's start here, end up, you know, in the sky. So absolutely amazing. And you know, thank you to everyone who has come along. We've really appreciated it. Really great to have a solid audience. And once again, I think that the NF token is a really good idea. So send me an email with your Ethereum addresses, and I can forward those on, and we can send you a certificate of participation, but on chain. So that's president@oxfordblockchain.co.uk. That's the email you want to send to. But yeah, I'm actually kind of blown away. The zero knowledge proofs tonight really got me, because I didn't know it was really a thing. You know, I thought it was a work in progress, but I didn't know it was real. You know, and people are doing it. So thank you so much, Laurence. And also, before I forget, don't forget to take up the information on XRP's website, particularly xrp.foundation. So yeah, thank you. Anything else, Laurence, you wanted to say?
Just thank you for organising all of this, and for everyone that came along. It's been a real pleasure meeting you all and doing these talks. Yeah, and I hope we'll all meet up one day when the lockdown is finished. Thank you.
Cool. But yeah, the slides will be up on Medium along with the YouTube recording. So take care, everyone, and have a great evening, and have a great week, rest of the week. So bye-bye.